Okay, so I've drawn a picture here, and it's a picture of a two sides of a box or a cylinder or something. There's gas in one side, and there's a vacuum. There's nothing on the other side. So the question is, when I open the valve here and just open it, what happens?
It fluxes gas.
Yeah, the gas goes flying over there because over here there was nothing. And over here there was a gas at some pressure. Okay? So what happened to the energy in this situation? So the energy of the gas, decrease, increase. Any thoughts? Well, if you do work, you have to push against something. Over here, there was a vacuum.
So there's nothing.
There was nothing to push against.
To the system?
No,
Or just, it just wasn't work.
Yeah,
Isn't it also because like there's like more volume, so then
There's less pressure?
yeah, less pressure and then less temperature and then temperature decrease.
well, it's we're going to try and figure that out. So the gas expanded there. It did not have to do any work to do it. So the gas expanded. It didn't do any work. The system can be isolated. In fact, let's isolate it from the world. Oops. Let's isolate it. Well, forget it. Let's just call that the whole universe. We won't even have a. Well, that might be confusing. Let's do it this way. Let's say I do that, so no heat can get in. Okay, I put it in some kind of. Essentially, one way to do that is remove the rest of the universe. So this is all there is in the universe, and then no heat can get in. There's nothing out there to give you the heat. The heat comes from moving particles. If there are no moving particles out here, but if I did that, would it still expand over there? Yeah, it would.
So it doesn't require heat to do that?
Or work.
So no internal energy change,
So
even though the
no-
gas expanded.
Yeah. Crap. So
That's weird.
so delta E.
Would it be zero?
I need to go to a thinner pen. I think I'll go to red if I do that too. Delta E is 0 because Q and W are 0. Okay? But it went over there anyway. So the question is, there's nothing in thermodynamics so far that told us if that would happen or not. It's a little disturbing, isn't it? Why does it happen if the energy and there's no heat flow or work flow? Yeah, there's something else. And the something else is very important. It is the entropy. So there's, and the way to think about that, in this case, is very statistically. So if you make it very simple, and just try to count the number of states the system has, we're going to say entropy is related to the number of states, and we've already seen that. So we don't have to write it down yet. Let's just count the states. So let's say I had one particle. One particle is boring. It can be on one side or the other. So there's one way to do that. If there are two particles, there's one way to have them on this side. There's one way to have them both on this side. There's two ways to have them on both sides. So if both sides are available, there's two ways to do it. If one side is available, there's only one way to do it. So we can write that 1, 2, 1. One way to do it on that side, 2 on both sides, 1 on the other side. And you can keep making this triangle here, and it follows the number of particles. So if I do 1, add 1 and 2 and get 3, add 2 and 1 and get 3, and add 1 and 0, I get 1. So in this case, 3 particles, there's one way to do them with all on one side, and there's 3 ways to do it with 2 on one side and 1 on the other, and 3 to do it with 2 on the other side and 1 on the other side, and 1 way to do them with all on the other side. Okay? And this scales with the number of particles. You can just keep doing this. So if you have 1, 2, 3, 4 particles, 1, 4, 6, 4, 1, 6 ways to do them spread out equally on both sides. And this scales this number gets way faster than you think it would. When you get to just 50 particles, this number in the middle here is already in the trillions. Yeah, oh crap. So the lesson is, if you look at the system and look away and look back again, it's in one of these states. It's easier to look here. The system is always in one of those states. Okay, they're all equally likely. There's no one different than any other ones. But I mean, they're all equal energetically, I guess is a better way to say it. Nothing is energetically different. But the states where everybody is spread out across both sides become ridiculously more likely. So you never see the ones out on the end, because it's 100 trillion times more likely, even with 50 particles, to see the ones where they're spread out. And if you keep going, of course, this gets stupid big. I mean, it's already 100 trillion at 50. Imagine going to a mole of particles. The number in the middle here is, 10 to the 2 to the 23rd, more than there are particles in the universe. So it's so likely to see the spread out state that you never ever see the end states. So the reason this happens is it's fine. There's nothing energetic. The gas could be here, but you never observe it because it's so much more likely to see it the other way. So that's kind of the story of entropy. Increasing entropy helps us understand why things happen, but it's really just a simple counting. There's no energy involved. There's nothing mysterious involved. It's just that's the frickin' more likely thing to see when you look at it. Okay? We do quantify it. That is, we give it a number. We say S is the natural log of the number of ways to do something. So the entropy of this state is ginormous. Entropy of this state is 0. There's only one way to do that. So natural log of 1 is 0.
So is S almost always a very, very large number?
Well, it depends on what your units are. I mean, if you're taking natural log of this, you express it in joules per Kelvin. They're reasonable numbers. So going from this to this is it's not a straightforward energy. So this is not an energy until you put it in energy units, and that will also heat over the temperature. So there it is. So if I asked you this, so did you see this in high school? I have a stack of cards.
Yeah.
And I have it in this state, and then I do this, and have it in that state. Which is the higher entropy state? And why is that?
Because it's in the most probable configuration. There are more configurations that there could be. But when it was in your hand, there was nothing making it go into this configuration.
Yeah, not necessarily. So I bring this up because this is a more subtle thing. This is one of the configurations you can have spread out.
Mm-hmm.
When it was in my hand, it was one of the configurations of all on one side. It was this one. This is one of these states. Okay? that state on the ground has one way to arrange it, just like that. So each of these things counts one arrangement. That's one arrangement. In my hand, it was also one arrangement. So the entropy of this state and that state are the same. Entropy is not what you thought of in high school. It's not spreading out unless the cards can rapidly exchange between the microstates. If these cards were flying around the room, then letting them go increases the entropy because they can occupy all the microstates of the room. That is just one of the microstates in the room, and in my hand was another microstate in the room. No entropy difference between them.
This is a more likely state than was in
No.
your hand.
No, there's no energetic difference. So that's like saying, when we went back here, if you had, let's see if we can erase some of the particles here and get down to a smaller number. So if we just had two particles, they could be on this side. So that's the stacked up in my hand situation. And they could be on, now we'll do it the fancy way, that configuration. Those are two configurations. They're energetically the same. Remember, nothing changed when those particles went over there. These are equally likely microstates. It's just when you start putting more particles in, the spread out has more microstates of the same energy, and that's where you find it. This, like I said, this is just one of the many microstates that the cards could be in the room. But when you look at just one of them, there's no entropy change between stacked up and that because the cards aren't moving. They're in that one state. The balls have to be able to switch back and forth, or this number becomes one. You're not exchanging between the number of ways, and it's just one of the ways.
So a deck of, like a half deck of cards with 26 would have less entropy than a stack with 52 because there are more ways the 52 can be arranged
Yes.
than the 26.
Yes.
Got
So
it.
if you have different amount of matter,
Understand.
then yes.
So
So
if
if
you
you-
added another particle here, you would increase the entropy of the whole system.
Yes, in general, entropy is an extensive property. It depends on the extent of the system. More particles, more ways to arrange things. That's what you're doing here. Okay? So these, the energy states have to be available. And they're all available here because there's no energy difference between them. So you can be in any one of them, and most of the time, they're in this one, spread out equally. So that is super profound again. There's nothing mysterious about, there's no mysterious force in the universe that makes this happen, that makes the gas expand into a vacuum.
It's just all relative.
It's just, it exists in the universe. When we look at it, it's always in one of these states. We can trap it in, a half state for a second, but as soon as we open it, then we see all the states because they're all equal energy. Everyone's equally likely, so this, which has the most combinations, is the one we see.